So in computer graphics, let us learn about 3D geometric transformation today. This will see the translation, scaling, rotations with quaternions, other transformations and coordinate transformations. So we have already talked about these aspects like translation, scaling and rotation along with their matrix and matrix conversion. So this is the transformation in 3D, okay? Transformation matrix. So this is 3 by 3. What is this? This is for scaling, reflection, shading, rotation. These values, these A, B, C, D, F, G, H, I, they vary. So depending upon the values which you put in here, scaling, reflection, shading and rotation will take place. In this one, this is for translation. Values for translation or parameters for translation are being placed here. And this is for your uniform global scaling, and this is your homogeneous representation, right? So these are all transformation in 3D in a nutshell for transformation matrix which you will employ. Okay, then 3D translation. We have already talked about the translation aspect of 3D, and in this particular case, these are the values. TX means translation for X, translation for Y, translation for Z. That means X, Y, Z, TX added to X, that is X dash is formed, or X dash is a new coordinate when some translation TX parameter is added to X. Likewise for TA, Y and TZ also. And what exactly it looks like is presented here. Now when you add this TX, TY and TZ to each coordinate, then the new translated position looks like this. And as I said in the previous slide, that these are the values which you place TX, TY, TZ, and if you multiply it with X, Y, Z1, where these are homogeneous coordinates, you multiply them and you will get the translated version or translated matrix. This is about uniform scaling. Means scaling, that means if this is a figure or this is a 3D primitive, then you scale it, but there is a uniform scaling in X, Y and Z direction. So if you closely see this matrix, this is Sx, this is Sy, this is Sz. So equal sharing, uniform sharing is performed by X dot Sx as Y dot Sy and Z dot Sz. Previous case, this scaling, this translation was addition. Here the scaling concept is there. So X is multiplied by Sx, we get a new coordinate X dash for each coordinate of X, likewise for Y dash and Z dash. This is relative scaling. This is not uniform scaling, but relative scaling. What does it mean? This is scaling with a selected fixed position. Scaling with a selected fixed position. This is your original position. Now we are talking about scaling with a selected fixed position. So first we translate it to this position, then, or say you are translated to origin, for example. Then you scale it. You know how scaling is done. So once you translate, you know what you are going to do. These are this is the matrix you are going to use. For scaling, what you are going to do. For scaling Sx, Sy, Sz, you are going to use. And then inverse translation. The translation, because you have brought these points or this primitive to the origin. Now you want to, after doing some certain scaling or the options which you have in your hand, you have to retranslate it. Means you have to inverse translate it. For that you are using -6, -5, -8. So what we are doing here is we are translating it first, okay, to the origin. Then what we are doing is we are scaling it, and then we are again translating or inverse translating it. So this is the matrix. You multiply it by X, Y, Z, and you will get the final version. Now we come to 3D rotation. This is the coordinate axis rotation. It can be along X-axis, it can be along Y-axis, or it can be along Z-axis. So there are general 3D rotations. That is rotation about an axis that is parallel to one of the coordinate axis, okay, like this, or this, and rotation about any arbitrary axis. So these are general 3D rotations. So coordinate axis rotation, which is around Z-axis, is given by this matrix, X-axis by this matrix, Y-axis by this matrix. So this is Z rotation, this is X rotation, this is along Y direction. So you have to really understand and learn by heart these values if you are really going to be working a lot in this subject. Then the order of rotations means order of rotations, this affect final position, how it is going to affect the final position. Because this is x-axis, you want to convert it or go along the z-axis or z-axis to x-axis. So what you do, you this is your original version. Now you rotate it along x-axis. So once you rotate it along x-axis, you'll get it like this. Now you will rotate it along z-axis. So what you'll get this way. So you'll get this. This is how you the order. Basically, the order is like this. Now see, this is the curved surface. And once you achieve the final position, when you rotate it around x and then you rotate it around z, the final position, this curve is here. So the final position is changed. In the same way, if this is z, you rotate around z and then you rotate around x. This is the final position, and the position is changed. In general 3D rotations, rotation about an axis or any axis that is parallel to one of the coordinate axes, this is called the general 3D rotation. So we translate the object so that the rotation axis coincides with the parallel coordinate axis. We translate first of all the object so that the rotation axis, it coincides with the parallel coordinate axis, and we perform the specified rotation here about the x-axis or any axis, x-axis, y-axis that is parallel. We translate the object so that the rotation axis is now moved back to its original position. I'll show you how. This is the original position of the object. This is the rotational axis which is parallel to the along with the x-axis. Now you translate rotation axis onto the x-axis. You have translated this axis onto the x-axis. Here, translation, and then you rotate object through theta. That is the rotation you want. And once you have rotated, you translate it again back to the position from where you bought it. That is the axis, you again transfer it back. This is the general 3D rotation about any arbitrary axis. Now, it can be any arbitrary axis which may or may not be parallel to your axis, x or y or z axis. This is the basic idea. What we do here is we translate this x1, y1, z1 to the origin first. Okay, this position. We rotate x2, that is x2, y2, z2 on the z axis. Say we want to rotate it along the z axis. Then we rotate the object around the z axis. First we rotate the this value on the z axis. When you rotate the object around the z axis, and then we rotate the axis to the original orientation. Then we translate the rotation axis to the original position. Same here. Okay. So this is first is your translation, then again rotation, and rotation. This is along z, y. These are different angles. Okay, and finally the translation. So this is how the rotation about an arbitrary axis is done. We are just translating it to the origin. Then we rotate on the z axis, then rotate around the z axis. Then we rotate the axis to the original orientation and we translate it. So this is the general 3D rotation. First, what we are doing is we are doing translation. So what we have done, this is the axis. Now we have we translate this axis to the x1, y1, z1, x2, y2, z2 to the origin. Okay. So this is the translation matrix. Then what we do, we establish some translation TR with respect to alpha in the x-axis. So this is the rotation with what we are doing here. These are the rotation matrix. So these are the points A, B, C. This, if you make a figure, this is the point, and you have now rotated it some alpha angle. This is the line. You have rotated it with the some alpha angle. So this is now the rotated point. So what will be our rotated point with respect to this ABC with alpha? The relationship is given by here. And now with this point, this is the projected point 0 BC. These are the projected point, and this point are the rotated point. So you can get the rotated version multiplying by this angle alpha, and you will get the values with respect to C and B only. C and B, because A is not involved here. We are talking about the projected point. This is the translation point. Then we rotate about y-axis by this phi angle. This is the projected point. This is the rotated point. Now you have more rotated point. This is actually phi. You can call it as beta. So let us take it beta. So it is rotation along rotating about the y-axis by say beta angle. Okay, so these are the projected points, these are the rotated points, and with respect to the beta angle that we are talking about, we have sine beta, cos beta. L is also there. Okay, this is the L, and D is also there. This is the D. Now what this rotation matrix will look like will be like this, and this cos beta in terms of A and D and L will be like this. So this is rotation about y-axis by some angle. And now rotation about z-axis by say desired theta. This is the desired angle, so you can easily apply this straightforward matrix. And then arbitrary axis rotation is involved. Arbitrary axis rotation. So we apply the reverse transformation to place the axis back to its initial position. That is T inverse, R inverse, Ry inverse. But what all we have done, we have to apply the inverse. So just take those metrics we have just defined and take the inverse. So finally, rotation about any arbitrary axis will be given by it. So even if you don't understand, you just have to understand this line. That will be enough. Let us take an example. Find the new coordinate of a unit cube. This is a unit cube 90 degree rotated about an axis which is defined by the endpoints 210 and 331. So we translate point A to the origin. Now you are going to translate this point to the origin. What points you have? You have these points 210 and 331. So you are trying to transform this 210, so that will be -2 -10, and this is the translation matrix for transferring this A point to the origin. So now we rotate this A dash B dash which we just got about the x-axis by a certain angle alpha until it lies on xz plane, right? So we have this 2 and 1. These are the projected points 0 to 1. With this we know this angle would be sin alpha is 2 by under root 2 square plus 1 square, and cos alpha would be 1 by under root 5. So we apply on L is also under root 1 square plus 2 square plus 1 square. L is there, sin alpha, cos alpha is there. So we have this rotation matrix as we just discussed in the previous slide. Then we rotate axis A dash B double dash. A dash B double dash. Okay, and this is A. This is our B double dash. So A B double dash about the y-axis and alpha angle phi until it coincide with the z-axis. So now these are the values under root 6, 10 root 5. So this is the alpha beta angle. We can get the sine beta, cos beta, and these are the 1 by under root 6. This is root 5 by root 6. That will be this matrix. So we rotate the cube 90 degree about the z-axis. For that, this is the simple rotation matrix for 90 degree, and then we apply this. Okay, so all this multiplication is done, and finally this is the rotation values for some theta. We can multiply r theta by the point matrix of the original cube like this, that is this one, and we can get the values of p dash. Now rotations with the quaternions, that is a scalar part s plus vector part v, abc. So the real part plus complex part, that is the imaginary values of ijk, is given by q is given by the scalar part and vector part. This is given by scalar plus ai plus bj plus ck. So real part will be s, and the arbitrary part, or say the imaginary part, will be given by ai plus bj plus ck. So rotation about any axis, we set up a unit quaternion, that is u, which is given by s will be given by cos theta by 2, and v will be given by u sin theta by 2. So we can represent any point p in quaternion notation like this: p is equal to x, y, z, which is the capital P is equal to 0, p, small p. We can easily represent any point position with the quaternion notation. This is the quaternion notation. So the rotation with the quaternion, we carry out with the quaternion rotation, that is q inverse will be s minus v. So p dash will be q inverse. We produce a new quaternion, that is p dash. P dash is equal to s square p plus v pv, 2s vp, v into p vp. So we obtain the rotation matrix by quaternion multiplication as we done in the previous case. So this is given by this matrix. So r theta will be nothing but t inverse mr theta t with the quaternions. So this is an example. We want to rotate about z-axis. We set the quaternions how: s is equal to cos theta by 2, v is equal to 0, 0, 0, 1 sin theta by 2. We substitute a and b equal to 0 and c equal to sin theta by 2 in this matrix, which is given by this matrix. We apply these two relationship to find this relationship or this matrix values. The other transformations also reflective related to the xy plane, z shear, z axis shear is also there. So reflection related to some, say, xy plane is given by x dash y dash z dash. You use -1 here, and for z axis shear you use AB here only. Then we come to the coordinate transformation. What about multiple coordinate system? You have local coordinate system, that is modeling coordinate system. You also have world coordinate system. So this is the local coordinate system. This is the world coordinate system. So coordinate transformation means, for example, you want to simulate a tractor movement. So a tractor moves, that is the tractor coordinate system will be there. Okay. Then this is the tractor coordinate system. Now you have this front wheel. Front wheel also have its coordinate system, which move in the world coordinate system. This is the world coordinate system. So front wheel rotate in the wheel coordinate system. The transformation of an object description from one coordinate system to another is coordinate transformation. The transformation matrix will be given by, we bring the two coordinate systems into alignment first of all. That is, we do the translation. The translation is done by -x0, -y0, -x0. Then rotation and scaling is performed. Okay, like this. You have uy, uz, means uy dash, uz dash, and ux dash, uy, uz, ux with dashes. So first we rotate them, we scale them, we align them. So we apply this relationship R. Okay. So this is about the 3D transformations, and we'll be seeing the outputs of the related topics in the later session. Thank you so much.